Okay, so we've been learning about the electromagnetism from last class, and I would like to review a little bit of the things that we have learned from the last class, and then we'll go into the second half of the chapter 10. So actually, when we look at the history of the physics, I think the first step was the Isaac Newton, right? So the Newton was around 1600, mid 1600 and the late 1600, and there was a Coulomb that's about 1770s, right? And he was the French physicist, and he developed the friction law. So that was we know that the shear strength of the soil, normal stress, times the friction coefficient mu, right? And we also use the tangent phi instead of the friction coefficient. And he's the one also developed the electrostatic law, the Coulomb's law, and the same person. Then, like 1830s, there was a Faraday, and 1855, there was a Maxwell, who combined the electrostatic law and the magnetic law. And there was a Rayleigh, and we have, this was around 1886, and we have our father Tae-Hyuk, that's around 1917 to 1960. Yeah. And Einstein was somewhere here. The early 1900s to mid 1900s. So the Newton derived the force F equal ma, right? From here, the elastic wave, the concept of the elastic wave starts. Huh? And there's a friction, and here you have, until the Maxwell, there was electrostatics. And the Newton was also the founder of the optics. And Coulomb also suggested the basic concept of the magnetism. And by the Maxwell, it converges, and he combined the theory of the electromagnetism. So this is a very brief history of the physics, and Newton studied the law for the elastic wave propagation and optics, and Coulomb studied the electrostatics and magnetism, and through the Faraday and the Maxwell, the three areas were combined into one theory. So from that moment, we can see the electromagnetic wave as a wave, and also the optics are the light is also the same. That the same concept of the electromagnetic wave can be applied to the optics theory. And Einstein, the particle, right? Etc., etc. So just one fun homework I would like to suggest is find the microwave oven, the mechanism of the microwave oven, right? 전자레인지. And so this microwave oven have a specific frequency that excites the water molecules, right? So if you put oil versus water, see if the oil gets hot, water will get hot, right? And probably the frozen chicken or any frozen food there's a defrost mode, right? And what's the difference between defrost mode and the normal mode? And make a mud bowl, wet mud bowl, and dry in air and dry in microwave oven and see the difference. And describe your observation on the drying process. Okay, and if we can move. So we've seen the basic concept or the theory of the static charge and the charge moving at constant velocity and the charge moving at time varying velocity. And here we can create a homogeneous electric field using some two parallel plates. Right? And then this will have the plus charge, this will have the minus charge. Then electrostatic field will be created to this direction, okay? Normal to the parallel plate. And the gradient of the electrostatic field, electromagnetic field here can be expressed as with the Gaussian theory, 1 over epsilon rho v, charge density of the free charge. Right? This is the Gaussian theory for electromagnetic field, electric field, sorry. So let's say that we have applied the potential of the 10 volt here, and the distance D is like 1 millimeter. In that case, the electric field is potential over distance, right? So 10 volt over 1 millimeter, that's 10 to the negative 3 meter. So 10 to the 4 volt per meter. This will be the answer, or the value of the electric field that's applied in between this parallel plate. And anywhere here, you have the same electric field. And what about the potential? Potential at this plate is the highest. So 10 volt will be, like, maybe I should say the 10 volt higher than the other plate. Okay? And then it's gonna gradually decrease to the lower plate. so that you have a constant gradient. That's correlated to the Poisson's equation. I'll show you later. And this electric field equation, the value that you just calculated is valid only there's no free charge inside this electric field. So rho v free is 0. So no materials between these two plates. Actually, this is the same with the capacitance or the capacitor. Capacitance. And we'll review this capacitance concept in chapter 11, I think, next week. So the electric field inside these two parallel plates are always the same value, right, regardless of the location. So the gradient over this electric field will be 0. Good. When you have a constant, the moving charge at constant velocity v, we can calculate the current I from the definition dq over dt. So the charge at a certain time, and if we do some manipulation, so we are inserting the dl over dl, then this dl is the same with the velocity, so dq times velocity over dl. So, and this becomes the equation dq times velocity equals I times dl. And if you want to create a homogeneous magnetic field, then you can have a coil, and in this coil we have constant current going in, and then you have a homogeneous magnetic field created. And this B is called the magnetic induction. And when you have a moving charge at a different velocity, time varying velocity, then you have change in magnetic induction with time. This becomes the electric field. This is the Faraday's law. And when you have a current, this can be related to the magnetic induction. That's ampere. And you have a time varying electric field. This also creates the magnetic induction. That's extra. And the Poisson's equation, we have two parallel plates, the electrode plate, and we are applying the voltage or the potential, electrical potential, to one side, and the other side is connected with the ground. And then we can, let me use the red one, we can draw the electric potential, and up to the left side electrode, you have a constant potential, and then there's a drop, and this will be a ground stage, right? So you have linear decay from one electrode to the other electrode. And here the gradient is the magnitude of the electric field, E. So the electric field is negative without dot. Gradient of the potential, electrical potential, and this will be constant in this geography when it's free space and inside the free charge if there's no free charge inside, the charge density is 0. From here, if we put the del operator, then this becomes this, and divergence of the E is rho v over epsilon 0. This is from the Gaussian law, right? From here, right? So Poisson's equation can be derived as rho v over epsilon 0. So again, if there's no free charge inside this parallel plate and this becomes 0, right? So del square v equals 0. So this becomes the Laplace equation, right? Rho v square, rho x square plus rho round vy round y square plus round v z round z square equals 0. Second derivative. And this is the same equation that we saw for the hydraulic gradient too. Like you have a total head distribution of the total head gradient over the space, then you have a CPG flow, right? So same equation can be derived. Laplace equation. Any question so far? So we just review very quickly that we have learned, and today we'll talk about the wave equation, and before that, I would like to briefly introduce about the polarization of the water. So DI water, or the deionized water, so we have several kinds of water that we can use for the laboratory experiment or in life. And there's a tap water, right, that you can get from the faucet, and deionized water. So it means that there's no ion, so conductivity, electric conductivity is almost zero. It's around 10 to the negative 6 Celsius per meter. And distilled water is, what is distilled water? So you boil it and you filter it, right? So it's a separated water. There's no impurity inside this distilled water. And de-aered water that we use for saturating the soil is, how do you can get there? So you vacuum it, or you can boil it. So when you boil, you are removing not all, but the most of the dissolved gas inside. So you can get the de-aered water by boiling, or you can just constantly vacuum the water, then you can get the gas out from the water. And stirred water is when you autoclave some water, then you can kill all the bacteria or the microbes inside, right? So stirred water means that it has no microorganisms. Eh? And we're gonna use the DI water, which is dielectric material. So the resistance, when you measure the resistance of this DI water, is almost infinite. It's really high. And also salt, like sodium chloride, for example. And when you measure the electric resistance of the powder salt or the just crystal salt, no current occurs. So it's an insulating material. Okay? So this is also dielectric. But if this salt is dissolved in the water, the salt gets ionized. So you have free ions moving inside the water. So that this becomes an electrolyte. And this can conduct the electric current. Then let's imagine that you have a water molecule in the two parallel plate. So, and at a certain point, you apply the electric field here. What will happen? Then you have an external electric field applied inside this two parallel plate, so that the water molecule will be polarized. Right? This has a dipole moment. So which one have the positive end, positive pole? Hydrogen side, right? So this has the positive pole, and oxygen side is a more negative pole, right? So this will be aligned to this direction. So this will be aligned like this. And if we think about the this accident, rotation of the water molecule, when we apply the voltage, so we apply the voltage, the electrical potential at a certain point, then because of the rotation of the water molecule and the polarization, you don't have the real charge movement, but it feels like you have a instant current occurring. So if you measure the current, you can detect the at a very short time duration that the current will spike. And the duration of this event is like very small, so it's a 10 to the negative 8 second, approximately. And then when it's all aligned, then you don't have any polarizability, the more molecules to be polarized, so that you have no current. And so the amplitude will be affected by the polarizability and the dipole moment. So if you have a more polar material, polar molecule, then you have more current occurring. If you have a less polar material, then the magnitude of the current will be less than that. Right? And the other thing is that you have a little bit of the time lag, and this is due to what? Because the water molecule also have the inertia, so it has a mass, so it takes time to rotate, right? And it's medium, so you have other molecules causing some friction. So also viscous drag also affects this event. So you have, this is affected by inertia and viscous drag. So if you can find I think it's the same with the resonance. Maybe at low frequency, water have they have enough time to rotate. Right? Probably at very high frequency, even though you apply some voltage for the electric field, water molecule have the big mass comparing to the frequency, so that they cannot move because the frequency are too fast. They're moving too fast, right? So there should be a frequency dependent behavior, right? Or the response, electrical response, with respect to the AC current, and that's this kind of a behavior can be captured by the frequency-dependent permittivity, K prime permittivity, or K star, sorry. K prime, the kappa is actually kappa minus kappa 2 prime. Permittivity. It's a complex number. And let's think about the ionized water. If we put the 2 electrodes into saline water, right, or the electrolyte, then when we apply the voltage, you have an anion moving to cathode and the cation moving to anode, right? And at the electrode, there will be a reduction and oxidation process. The reaction occurs so that they can exchange the electrons. electron exchange. Then when we apply the voltage like we did for the deionized water, what will happen with the current? When you apply the voltage, you have increase in current, and then it's gonna decrease to a certain point. And this certain point reflects the redox reaction. Of course, you have some water molecules, right? Aligned and polarized too. Any question so far? Right. So from this rotation of the dielectric material, we can get we use the parameter called the permittivity to describe this polarizability. And if you imagine, instead of the electric field, if you imagine you apply the magnetic field, then also the magnetic material will rotate and move, right? And so that character can be captured by also magnetic permeability. Right? And because the electric field and the magnetic field created together always. Then these are the equations that we reviewed in the last class. And from that, so for example, from the Ampere and Maxwell relation, here, if we differentiate the Ampere-Maxwell relation with respect to time, then you put the round t here, right? And here also round over round t. Then it becomes this equation. Right? And from the Faraday's law, what was the Faraday's law? Faraday's law was this one. Right? So dH over dt is related to the curl of the E electric field. So d over dt, this becomes this one, so that if you put it in here, and then you can derive the equation for electric field. Actually, it's an electric wave equation. And when you look at the equation, this is a second gradient, second order of the gradient of the electric field, and it's function of the magnetic permeability and electrical conductivity and the permittivity, right? And similarly, we can also derive the magnetic wave equation. So the variation in magnetic field in space and time is like this. So it's perfectly the same equation. So let me move in. Then the electric field polarized in y direction considering a plane, electromagnetic wave propagation in x direction. So like this, the electromagnetic wave propagates in x direction, and then you have an electric field generated in y direction, and also the magnetic field is generated in the z direction. So this electric field and the magnetic field are normal each other and perpendicular, and these both are perpendicular to the direction of the propagation. And this electric field can be also expressed with this equation. It's Euler's form, right? So it's a harmonic equation. You have omega t and the gamma star times x. Here the gamma star is the complex wave number. So this is actually the same equation that we use for the elastic wave propagation. And this gamma star is called as propagation constant. So as you can see, this is because it's a complex, this gamma star is alpha plus j beta. You can express it with this equation. And then this figure shows that when you have a discharge of the electron oscillating between these two electrodes, then you have an electromagnetic wave going to z direction and magnetic field and the electric field. And the spectrum, when we look at the spectrum, depending on the frequency, I think this is just give you the idea about the frequency range of the electromagnetic wave. This is the visible range. Visible range is 10 to the 14 and to 10 to 15 hertz. Infrared is below than that, and the ultraviolet is larger than that. And the X-ray, hard X-ray, and the soft X-ray, gamma ray is 10 to the 16, larger than 10 to the 16 hertz. And microwave oven uses around gigahertz, right? So the GPR, the ground penetration radar, range is set here around. And the IP measurement, the induced polarization measurement, is around less than kilohertz. And FTIR, the one that you use for the chemical analysis, is in this range. And look at the wavelengths. So the wavelengths indicates the scale of the wave, right? The wave can detect. And the bacteria is in here, visible range, virus, protein, the water molecule, here is a 10 to the negative 10, so it's less than 1 angstrom, nanometer, and that's the range of 10 to the 18 hertz. Okay, another figure shows the spectrum, and if the medium is free space, then complex permeability, magnetic permeability, is the same with the mu naught, and also the dielectric constant is the same with the epsilon 0. Then you know that this mu naught and the epsilon 0 are constant, right? The 4 pi times 10 to the negative 7 Hahn per meter, and 8.85 times 10 to the negative 12 Faraday per meter. And if we calculate the speed of light, in free space, and that becomes around 3 times 10 to the 8 meter per second. And you can calculate this one from 1 over square root epsilon times mu naught. Let's see if it's really similar range. 4 pi 10 to the 7 times 8.85 10 to the 12 square root to the minus 1. This is 12, 8, around 100, right? So if you just use the 3, 12 times 8 is 96, so that's around 100. So then 10 to the negative 10, right? 17. How much is it? And then 17. Oh yeah, that's around. Yeah, I think it's similar. Yeah. So if you plug the number, the epsilon naught and the mu naught to here, this equation, you can get this number. Right? So the polarization of bound charges and magnetization of the medium are produced by forces and torques from electric and magnetic field. On the other hand, the inertial and the viscous force oppose these applied forces and torques. So electromagnetic properties of material are frequency dependent, like that we just show you with the water molecule inside these two parallels, two plates, parallel plates. And the response can be out of phase with the excitation. So then you have to capture the amplitude change and the phase shift, right? And to capture these two parameters, we can use the complex number. So it's like the same. The concept remains the same. Concept remains for the elastic wave. So when you have a spring, when you apply the force, that the force and displacement curve will be just linear like this. Right? You don't have the loop. So then in the time domain, when you look at the time domain, when you apply the force, sinusoidal force, F, then the response will be in phase, will be in the same phase, right? Only the amplitude changes, right? And as soon as you apply this damper, then your response will be like this. So then inside this area is correlated to the damping ratio. Right? So you have now viscous drag and the energy loss. So then when you plot it in the time domain, if this is the force and if this is the deformation or the displacement, and there will be a time shift. Right? So that we use the K complex number, K star, instead of just K. Right? And this K star is K prime plus I, K, let's use the J times K2 prime, double prime. Then it's the same. So I think when we put the non-polar molecule inside this electrode, then the rotation will be, the polarization will be very small. Because it has non-polar, is non-polar. And this is the polar molecule. And when you apply the electric field, it's gonna rotate. But as we just said, it takes time to rotate and to be polarized. So this behavior will become the frequency dependent, and there will be a phase shift, so that you need to define the complex number, and that's the complex permittivity. And another parameter is the sigma in the wave equation. Right? So when we look at the wave equation, there's a sigma and the epsilon and the mu, right? And this is a complex number, and mu is complex number, but the sigma is only the real number. And this indicates the DC conductivity, and it's the same with the standard conductivity that we use for the normal life. And it's a real quantity. And magnetic permeability is complex number. Question? I'll just give you some time to write it down. Okay, can we move on? So complex permittivity is defined where is it? As this one. Right? So you have a epsilon prime and the epsilon double prime, and the permeability, magnetic permeability, also complex number, and mu prime and the mu double prime. And this indicates the polarizability, and this indicates the magnetizability. And normalized with respect to the values of the vacuum or free space. So you can divide this permittivity using this epsilon 0, the magnetic permeability with the mu naught, then it's called the relative permittivity. And relative permittivity is epsilon star over epsilon 0 or the epsilon naught, and we use the kappa. Kappa prime and the kappa double prime. And for the relative permeability, we just use the mu rel, so mu sub rel, and mu rel prime and mu rel double prime. So for non-ferromagnetic material, relative permeability will have only the real value, and that's going to be the same with the identity, the 1. So the mu rel prime is the 1, and mu double prime is 0 in that case for non-ferromagnetic material. And as long as your soil doesn't contain the iron or the heavy metal, only might consist of the silica or the silicate mineral, then your soil will be non-ferromagnetic. Or the quartz dominant soil or like clay dominant soil. Standard conductivity, so it's a repetition. Again, it's a zero frequency current so you apply only the direct current, and then you measure the resistance or the conductance. From there you can calculate the conductivity and real quantity without the out of phase component. And out of phase component of the permittivity, so out of phase component of the permittivity is what? Imaginary value, imaginary component of the permittivity, kappa double prime, is in phase with conductivity. So this is very important observation. So losses due to polarization and conduction are measured together. So when you measure the complex permittivity, then you have a real value and the imaginary value. But imaginary value always captures the DC conductivity together, right? Because they are in phase. So the effective imaginary permittivity can be defined as a function of the pure polarization component and also the conduction component. So it's the ohmic conduction component. So here we just use the effective term to define the imaginary measured value of the imaginary component. And likewise, we can also define the effective AC conductivity. So instead of just using the direct current, you can use the AC current, alternating current, to obtain the electrical conductivity, right? In that case, you capture the also the polarization effect. So, you can see that you have a sigma, which is the DC conductivity, and you have a additional term that's a function of the polarization. And loss tangent delta is defined as the effective imaginary permittivity over real permittivity. If the tangent delta is larger than 1, it's called a lossy material. If it's less than 1, it's a low loss material. High loss and low loss. Okay. And then from the Maxwell equation, we derive the wave equation. The wave equation is this one for the electric field, right? And if we substitute the E with the E naught times this Euler equation, right? Exponential function of JWT or J omega T minus gamma star times X, then this gamma star will be a function of mu and sigma and the E, right? The epsilon, the permittivity. So mu, this should be epsilon. It's typo. I will show you the full equation of this gamma star, but because it's a complex number, we can just simplify with the alpha and beta, right? Alpha plus j beta. Then we plug it here, and then it becomes this equation. The second one here. Then you can split the attenuation factor, e to the minus alpha x, and you have the oscillating component. So before in the wave equation, it was, what was it? I think it was the same, right? Minus alpha times E J omega T minus, I think instead of the beta, it was kappa X. So this was the equation for the elastic wave. You can see that the similarity between the elastic wave and the electromagnetic wave. And instead of the kappa, because we use the kappa as a permittivity in this chapter, so instead of that, we just use the beta. Right? So here the beta is the same, equivalent to the kappa in the elastic wave equation. So the beta is the same with the wave number. So equivalent to kappa. And alpha is what? Alpha is the logarithmic decay, right? Here, minus alpha x. So alpha shows the attenuation. So the real value of the gamma star, the gamma is what? Propagation constant. So the real value of the propagation constant is the attenuation. And the imaginary component of the propagation constant gamma star is related to the velocity, or the group velocity to be specific. So when you use the wave number, the beta, then omega over beta gives you the phase velocity. So this will be the phase velocity. I think this is, we have covered the most of it, and it's broken. If you solve this equation here, or if solve this wave equation using this this electric field substitution, then you get this equation. So gamma star is function of conductivity, permeability, and the permittivity, and the angular frequency. And for non-ferromagnetic material, I think mu, this is the, sorry, mu star is same with mu naught, and is it epsilon? Does it say anything? Oh, so my screen is only broken. No? Yep. Epsilon star is epsilon 0, kappa prime minus j, kappa double prime. So that's according to the equation. And the c naught is the speed of light in free space, right? Then you can derive this equation, right? And then the velocity is, as we said, the phase velocity is omega over the imaginary component of the propagation constant, gamma star. And for non-ferromagnetic medium, then it can be simplified to this one. And then from that, if the conduction laws are also ignored, then the sigma is 0. Then if the sigma is 0, this part becomes 0, so this will be only the kappa, and kappa plus kappa is 2 kappa and 1 over 2, so this will be c over root kappa, right? Square root kappa. So this can be, this equation is valid when you have the dielectric material and non-ferromagnetic material. For example, DI water, or what else? Wood, plastic, right? That kind of it. And then let's calculate the wave speed in water, in deionized water. So if the kappa, this is the kappa prime. Kappa prime is the 80, and the sigma, the electrical conductivity is 0, and the imaginary component is 0, then how much is the speed of the wave in deionized water? 얼마가 될까? 대략적으로. 1/10 of the wave. So this is 9, so I think the 9th of it, right? So the light of speed becomes slower by 9 times in water. And the refraction index N, this is in Korean 굴절률. Refraction index is the velocity ratio between the free space and in the media. So, do you remember the prism? You have a light coming in, and this becomes scattered, and then you have a spectrum, the visible spectrum, right, in the prism, and that's because of the different refraction index according to the frequency. Frequency dependently, you have different refraction. And for the non-ferromagnetic and the low risk material n square, I think this is the real kappa prime. Right? Okay, and the attenuation coefficient was the alpha in this equation, right? So then alpha is the real value of the gamma prime, and you get this equation for non-ferromagnetic media. And here, when you look at it, you have a real component of the permittivity, and this is the effective imaginary component. So it captures the polarization factor and also the ohmic conduction factor. So losses come from ohmic conduction and polarization. Even if the medium is non-conductive, the sigma is 0, the attenuation coefficient is not 0. So you have, if this is 0, still you have a kappa prime and the kappa due to the polarization losses captured in kappa double prime. And skin depth, the depth at which the field strength of a plane wave decay to 1 over E. So this is the same. And then X this is the skin depth. Good. And this is the summary. The static charges cause the electric field, and electric field implies the presence of charges, and two nearby opposite charges from the moving charge produce the magnetic field, and charge acceleration or time varying current generates the time varying electric field, and time varying electric field vice versa creates the time varying magnetic field. On the other hand, the time varying magnetic field produces time varying electric field. So they are all linked together, the electric field and the magnetic field. Maxwell equation predict electromagnetic waves and electric and the magnetic field varying normal to each other, and transversely you have transversely to the direction of the propagation. And these electromagnetic properties of the medium there are three parameters, right? Permittivity and conductivity and the magnetic permeability. Propagation of the electromagnetic wave in material depends on the electric and magnetic property, and reflection and the refraction at interface depends on the properties of two media. So like that we calculated the impedance for the mechanical wave, you can also get the Z value, and so there will be a reflection and the transmission and refraction coefficient.